So I'm going to talk today mostly about things that I haven't really done yet. It's partially motivated just by the spirit of the program I've been involved with here in the last week, which is focusing on open problems and future prospects. And also motivated by my new position as an assistant professor at Queen's College, where I'm starting up a new research group to work on white dwarf stars. And I'm going to tell you a little bit about one of the longer term projects that I'm able to think about now that I'm out from under the really short term postdoc contracts. Yeah, I'm here to tell you about our activities and to seek some new collaborations and input on these ideas. So just to introduce us a little bit, these are the students involved in the new CUNY Queen's College Astronomy group, where we're focusing on observational time domain stellar astronomy with a definite focus on white dwarf stars, working on projects related to the study of pulsating stars, trying to stereoseismically constrain their properties, looking for exoplanets around white dwarfs, and developing just new methods and open source software for doing time domain analyses. So my students, Andrew Dublin's a PhD student who's working on computing stellar models and pulsation properties to understand how well we can constrain white dwarf structures in the modern era of time domain precision light curves from space and astrometry from Gaia. Niku's been on a PhD rotation with me. She potentially will be carrying out much of the work I'll be talking about in this talk. Andrew Ayala is a master's student who is computing patterns of pulsations on the surfaces of stars and modeling the effect of eclipses passing in front of these, so we can potentially do eclipse mapping for pulsational mode identification. Yao is exploring the effects of distant planets around white dwarfs and how they affect our measurements of pulsational rates of period change and the things that we infer from these measurements. And Swan has been fitting contamination factors for the large 23 arcsecond test pixels to determine how well our understanding of that, or how much our understanding of that might affect systematically our inferences of things like transit depths, eclipse depths, any sort of signal heights. For most people, when they think about planetary transits, maybe not you guys, they think about something like this, an Earth-sized planet passing in front of a sun-sized star, something along these lines. Here, this Earth is the black dot, not to scale to the Earth's orbit, but this causes a small decrease in brightness as it blocks out part of the star, just 100 parts per million decrease in brightness. So we need precision light curves from space to hope to detect something like this over multiple eclipses. If we replace the sun with the white dwarf that it will eventually become, then we just don't get eclipses anymore, right? This is the main problem for detecting white dwarf transits and planets. White dwarfs are just very small targets to pass in front of, and that's why this field is lagged behind other exoplanet studies. But if we shore up the orbit a little bit and bring the planet a little closer in, we can make the white dwarf be transited. And the transit properties are very different. Instead of 100 parts per million decrease in brightness, for this scenario, there's like a 70% decrease in brightness. And you can imagine for most planets that are larger than Earth's, there could be even a total occultation of the white dwarf, causing us to not measure any light in this moment. And that's why I'm carrying out this project called the Disappearing White Dwarf Survey. We're looking for these moments when white dwarfs are deeply eclipsed or transited. And these have very different properties than regular transits, right? They're very deep, so we do not need precision space-based photometry to make these detections. However, there's all these difficulties all related to white dwarfs being small. They're intrinsically faint. The transits only last like a couple of minutes. The orbits have to be extremely edge-on from our point of view in order for the planet to pass in front of the white dwarf. and the planet has to be pretty close into the white dwarf in order to have a reasonable geometric probability to transit. But these challenges are beginning to be overcome by some of the data that we have available now. And that motivates this disappearing white dwarf survey, which is an effort to systematically identify and characterize all the white dwarfs that disappear or dim very significantly in photometric surveys. These will be transiting exoplanet systems, as well as white dwarfs eclipsed by fainter white dwarfs, white dwarfs eclipsed by cool M-dwarf companions, or white dwarfs eclipsed by brown dwarfs. And to do this, I'm focusing on recently available data sets. The first that has been transformative to our field is the Gaia data set, which has revealed hundreds of thousands of white dwarfs down to a magnitude of about 20. So we know which stars to look for these deep transits from. And also the Zwicky Transient Facility, which is observing the same fields over and over in the northern parts of the sky some 1,000 times. So there's a lot of opportunities to catch a snapshot right in a moment of a deep transit or eclipse. So I'm going to demonstrate the approach that I've been taking for this, but I'm going to do it with some really nice figures from Jan van Rostel's work, characterizing a brown dwarf that eclipses a white dwarf, because they're nicer than my plots. So he's giving the next talk, so he may tell more about this. So the first step is just to identify moments, snapshots from ZTF when a white dwarf is significantly fainter than its normal magnitude. So here's some ZTF light curves in 3 different filters, and you can see these eclipses, they're phased up to the orbital period. If a planet or another star is going to eclipse a white dwarf, it's going to have to be in a very short period orbit for that to be likely to happen, probably just a few hours or less than a day. So we can typically confirm these eclipsing systems and resolve the shape of the transits or eclipses with just a few hours of data with high-speed photometry. So here's an example for this system. And then we still need to know what the nature of the companion is. And to do this, we like to have a constraint on the mass from radial velocity, which you see here. So for this brown dwarf, it creates a radial velocity variation about 24 kilometers per second. Each of these steps has its challenges. I've been trying to develop strategies for dealing with. The one I've really learned about the hard way over the last couple of years is that when you're looking at like a trillion star detections and trying to filter that down to what you're interested in, well, there's going to be some bad measurements. And when you're looking for the most extreme outlier measurements from these light curves, it's going to uncover like a bunch of junk that you've got to work with. So most of the time when I look at a ZTF light curve and it shows a very faint measurement, and I go look at the, I think it's always a good idea to put your eyes on the images because most of them look something like this, where there's some light, I don't know, trailing away along a column. And so the photometry returns a significantly fainter measurement than usual. So to deal with this, I've been working with a bunch of undergraduates and high schoolers, especially over the summer. This next summer, we're going to be going through a whole bunch of candidates and confirming the quality of the measurements to develop a catalog of all of the visually verified deep transits or eclipses in the ZTF public data. So the next step is something I've been working on the last couple of years. I've been acquiring some high-speed photometry of white dwarfs that I visually verified the quality of the ZTF data for, and here's just 4 examples. You can see the white dwarfs disappearing from the images, right? This is the disappearing white dwarf survey. I think this is such a cool thing to see and very compelling for the public. I love to show these. Yeah, this is what we're going after. And the next step that I haven't gotten very far with yet, and I'm kind of interested in help from the room, is following up with the radial velocity. We need to, so the broad spectral lines of white dwarfs won't shift very significantly if the companion mass is of a planet. And so we can really put limits on what type of systems these are with radial velocity. I'm planning to apply for some time on Gemini with this, but I'm also very interested in what SDSS-5 can do. I don't know the details of this, but I've read about this White Dwarf Chronicle, not much information online about this, but besides that they're going to get three spectra of every white dwarf down to 20th magnitude in the north. So this will really allow us to see what our radial velocity variables are not. I'm not part of the Sloan 5 consortium, but I really want to urge those who are and who are going to be looking for radial velocity variations to not only publish those variations, but to publish the non-detections, which will be incredibly valuable. So I'm not the only one who looks for things like this in the ZTF data. Here are a few other recent efforts, but the main difference is that these are periodogram based, looking for periods of repeating dips, whereas I'm looking for individual dips in brightness or even dropouts where the ZTF doesn't detect the white dwarf at all because it's disappeared. And so for that, we look at the survey metadata and try to determine when a white dwarf should have been measured, but wasn't. This may sound dumber, but I think it's just simpler, and that's one of its virtues, because this will allow us to better understand the underlying populations for these disappearing white dwarfs. How many of them are binaries of different types? How many of them are planets? Which is very important to know because we're about to get a whole lot more data of the type that ZTF is providing with the Vera C. Rubin Observatory, which will observe in 6 filters for 10 years, beginning in 2024, down to magnitude of 24.5, which is just too faint to do the kind of follow-up that we're talking about here. So to understand that, we may expect from tens of millions of white dwarfs observed, possibly up to thousands of white dwarf transits, many more times that many eclipses. But these sort of studies that have predicted this have presupposed that we know where the white dwarfs are. We know this for the brighter ones from Gaia, but to work out where those stars are from for these fainter stars, we may need to use the Vera Rubin data themselves, which will extend the parallax sensitivity of Gaia down to fainter magnitude and provide proper motion information as well. And so this is one project idea that's kind of come up over the last weeks here at KITP. Me and Nicola Gentile-Fusillo will be exploring the sensitivity of the ZTF data to reveal the white dwarfs that it's observing based on some simulations that the Vera Rubin project provides. So stay tuned for some results from that in the near future. I'm sure you're all interested in how we'll know where the white dwarfs are in LSST. And that's just a little preview of some of the long-term goals of the newest white dwarf group at Queens College. We're really excited to have this new presence in the field, and we look forward to collaborating with you all on all sorts of exciting science in the future.
So how many eclipsing systems have you found so far? And based on the colors and duration, are they mostly M dwarfs? That's what I would expect.
Yeah, lots of M dwarfs. I haven't done a lot of detailed analysis of the colors. That's something I need to work on more. Yeah, most of them, if I find them in the data, they're known systems. So for the most part, yeah, they seem to be, eclipsing M dwarf systems. With my follow-up of the systems that I don't know, there's about a dozen eclipses I found, but then Alec Kosakowski published some of those before I got to them. So yeah, one thing I'd really like is more like open collaboration, so we're not duplicating observational efforts. That's also why I put this emphasis on the multi-epoch spectroscopy that SDSS will find. This is going to be proprietary, but it's so valuable to keep us from like duplicating observations on Gemini or something like that. I would hate to waste time on these oversubscribed facilities. So that's something I'm really curious about, what that's going to be able to do.
A planet that is too close may not survive the red giant stage, right?
Yeah, sure.
So what do we expect?
Yeah, well, it's hard to say what we expect because we don't have a lot of examples. We don't know the occurrence rates, which is what we'd like to figure out from this type of analysis. I don't expect to detect planets that were originally close into the white dwarf, but they do have to be close into the white dwarf now in order to have a high likelihood of transiting. But we have all these examples of transiting planetesimal debris, atmospheres that are polluted with metals that should disappear below the photosphere, that imply that there's ongoing accretion of planetary debris happening now, debris disks and so on, as well as many theoretical works that show different processes that could cause planets to migrate in towards the white dwarf at late stages. That we hope that there are some planets close in so we can discover these. So it's not really known what. I've done some simulations of like, based on different planet occurrence rates, how many we would expect to find. So if we assume that like maybe 1% of white dwarfs has a planet at less than a 1-day orbit, then we might expect in ZTF to discover like 5 to 10 transits. That's sort of.
So just a quick comment, there's one transiting planet among the closest 300 white dwarfs with a period of 1.4 days, so there's hope.
Yeah, I just wanted to add, I think it's really great that you're just looking for the dropouts and not using the periodogram-based techniques, because really for the periodogram-based techniques, you need something like 5 samples in Eclipse.
Yeah.
And for planets around white dwarfs, even at 1.4 days, like that example, the duty cycle becomes so low that in ZTF, there just weren't enough samples to pick it up.
Yeah, right.
And a suggestion I was going to have for you is, TESS is actually pretty powerful because of its sampling. And something I've successfully done is picked out a system where there were only 3 in-eclipse points in Atlas. But then using the test data, I was able to, with fidelity, pick out the actual period because it had the sampling necessary.
Yeah.
So you can kind of also combine some of these data sets and play tricks like that if you've got a solid candidate.
That's a great idea. I think we could do that probably for those that are brighter than 18th magnitude, maybe something like that. Yeah. Down to what? Really? Yeah. Oh, okay. Yeah, I guess it's a big dropout signal.
Square root event statistics.
Okay.
If there are no further questions, let's thank Keaton again.